Hi guys, welcome to Namsin YouTube channel. I'll be taking complex analysis today, analytical function. So what do we mean by when a function is analytic? So let f of z be a single valued function defined in a region R on the what? On the z plane. Then f of z is said to be what? Is said to be analytic if f of z is said to be analytic at a point z0 if f of z is differentiable at z0 and in its what? In its neighborhood. So what do I mean by its neighborhood? Like, assume you have this z plane now, and this is z0, such that the distance from here is epsilon and epsilon. So this is, so z, the function f of z is analytic at z0 if it is differentiable not only at z0 but in its what? Epsilon what? Neighborhood. So you ask yourself that what does it mean for a function to be what? Differentiable. A function is differentiable if it satisfies this, that is, if the limit exists, the limit as z0 tends to 0 of what? Z plus delta z minus f of z over what? Delta z. So if this limit exists, f of z is said to be what? Differentiable. And note, the differentiability or the way in which f of z or delta z tends to 0 is independent of the path. Assume this. Assume we are going to this point. We have f of z. So at delta z tends to 0, if we go through as a curve, as a line, through the x-axis, through the y-axis, we will get to the same limit on the what? On the complex plane. So it does not apply on the real plane, but on the complex plane, irrespective of the direction of the limit, you get the same answer. So the limit is independent of the path. That's the first thing. So I will move further to what an entire function means. So let C be the complex plane and what? And f of z be a function defined on C if f of z is differentiable everywhere in C, then f of z is said to be what? Is said to be what? Entire. So a perfect example of an entire function is what? The exponential function. So we have what? Examples. So we have the what? Exponential function, which is differentiable everywhere in what? On the complex plane. And that one is the what? The sine, the cos, the tan function are all what? Differentiable on the complex plane. And that one are polynomial functions. They are differentiable everywhere in the complex plane. So if a function is not analytic then it is said to be what? It's said to be what? To be what? Singular. So if a function is not analytic, it will be singular. If it's not singular, it will be analytic. So now, we have some set of conditions that the necessary and sufficient conditions for a function to be analytic is 1. The Cauchy-Riemann equations are what? Are satisfied. Then 2, the first partial derivatives are what? Are continuous. On the complex plane. So, and okay, let's talk about the Cauchy-Riemann equation. So now, since we are talking about functions, so assume we have W, which is equal to what? A function of Z. So we are saying Z is a what? A complex number. So obviously, a function of Z, a function of Z will be what? Also a complex, will be a complex number, such that U and V are what? Functions of X and what? And Y. So W can be written as U of X, Y plus I V of what? X, Y. So now, function W satisfies Cauchy-Riemann so we have that the U, the X is the same thing as what? The V, the Y, and the U, the Y is the same thing as minus what? The V, the what? The X. So these are the Cauchy-Riemann equations. So this is a necessary condition for a function to be analytic. So if we satisfy this pair of equation, that is the partial derivative of the function U with respect to X, which if it is equal to the partial derivative of function V with respect to Y, and also if the partial derivative of U with respect to Y is equal to minus partial derivative of V with respect to what? X, then it satisfies Cauchy-Riemann. That is just a necessary condition. So if we move further, that if the first partial derivative are continuous on the complex plane, then W is said to be what? Analytic everywhere in the complex plane, or said to be analytic at point Z0. So now, my aim here is to prove this Cauchy-Riemann equation. So, since you said W or f of Z is said to be what? Differentiable, then what does that mean? We have that what? W prime or f prime of Z is the same thing as what? The limit at delta Z tends to 0, f of Z plus what? Delta Z minus f of Z over what? Delta Z. So you know that the derivative, as I said, W prime, I want to find the derivative, that's W prime, because what? F prime of Z. Then this is this from what I wrote earlier. Then since f of Z is also, since W can be written as this. Also now, let's look at what I will write. So I can write this as delta X tends to 0 and delta Y tends to 0. Since I can write Z as a function of what? X as this. So if delta X, delta Z is the same thing as what? This plus what? I delta what? Delta Y. So then I will have what? U of what? X plus what? Delta X, comma, Y plus what? Delta Y. Then plus I V of what? x plus delta x, y plus delta y over delta x plus I delta y. Then don't forget, then this one will be minus u of what? X comma y plus IV of x comma what? Comma y. Perfect. So now, case 1, move with me. So case 1 will be, so we are assuming that we're taking delta y to be 0. So, and let delta x tends to what? 0. Since I mentioned earlier that if you are finding limits on the complex plane, it is what? Independent of the path. So taking delta y to be 0 and make delta x tends to 0. So we have that. So the derivative becomes limit as what? Delta x tends to 0 of what? U of x plus delta x, comma what? Y plus I v of what? X plus delta x, comma y, then minus u of what? X comma y minus b of x comma y, then over what? Delta x. I just open the bracket and there's minus. Then I can split this and we have limit of delta x tends to 0, ux plus delta x comma y minus u of x comma y over what? Delta x. Then plus limit of delta x tends to 0 of what? Then I can put I here, makes sense. Then v of what? X plus delta x comma y minus v of x comma y over what? Delta x. So clearly this becomes what? Du partial derivative of v with respect to what? With respect to x plus I partial derivative of v with respect to what? With respect to x. We name this equation what? Equation 1. Now case 2, you can have that. Why not assume, since it is independent of path, you can also have that delta x equals to 0 and make delta y tends to what? 0. Then the derivative y prime becomes what? Limit as delta y tends to 0 of what? U x comma what? Y plus delta y plus IV of x y plus delta y, then minus u of x y minus v minus IV, okay, yes, minus IV of x comma y delta, this is what? I delta y. Very good. So now, since we have written this, now the next thing is the b prime is the limit at what? Delta y tends to 0. Then we have what? U of x comma what? Delta y plus y. Then minus what? U of x comma y over I delta y. Then plus limit as delta y tends to 0 of what? V x comma y plus delta y minus v of x comma y over delta y. Now you'll be wondering where the I went to. So if I factor out this I from this E, then it will have cancelled out with this one here. Then the other one for the U, that's why I have as this I as the denominator here. Then I know that this clearly is just 1 over I delta U du dy plus the V the what? The v, the y too. Then obviously if I rationalize this, I'll have what? Minus I du dy plus dv dy. Name this what? Equation 2. Since we are telling us that the derivative is independent of the part, or the limit is independent of the part, then I can say boldly that minus I du dy plus dv dy is the same thing as du dx plus I dv dx. So comparing both sides of the equation, we have that dv or du dy is the same thing as minus dv dx, and du dx is equal to what? Dv dy. So these are the Cauchy-Riemann equation. So if this satisfies the Cauchy-Riemann equation, then the function is, we can say function is analytic, but we can't just conclude. Then if we move further, that if the function, the partial derivatives are continuous, then we can conclude that the function is what? Analytic. Now let us take an example. Now we want to show that this function is analytic everywhere on the complex plane. So now the first thing, the necessary condition is we need to show that f of x, y satisfies what? The Cauchy-Riemann equation. That is du dx the same thing as v dy, and du dy the same thing as what? Minus dv dx. So now, we are saying let f of x, y be equal to what? U plus iv. So we can compare that. So that means we can say u is equal to what? X squared minus y squared, and v is the same thing as what? 2xy. So now du dx is 2x, du dy is what? Minus 2y, dv dx is what? 2y, and dv dy is what? 2x. I'm just taking the partial derivative of x with respect to partial derivative of v with respect to x, partial derivative of v with respect to y, partial derivative of v with respect to x, and partial derivative of v with respect to y. So clearly du dx is equal to dv dy, and they are both equal to 2x, and du dy is equal to minus dv dx equals to what? Minus 2y. So then Cauchy-Riemann equation is what? Is satisfied. Then the function f of x, y is analytic also. We can conclude that the function is analytic because the partial derivatives are all continuous in the complex plane. Then we can conclude that what? F of x, y is what? Is analytic. So you should know that the fact that it satisfies Cauchy-Riemann does not necessarily make it analytic. But if it is analytic, it will obviously what? Satisfy Cauchy-Riemann. So if they give you a function to check for the analyticity, just have to just show that it satisfies Cauchy-Riemann and the partial derivatives are continuous. I made mention of something. If it is analytic, it will satisfy Cauchy-Riemann. But if it satisfies Cauchy-Riemann, does not necessarily mean it is analytic. Thank you.